All right. Hi, my name is Lillian Mcpadden. I am a current senior at Marist College in my undergraduate studying computer science, and this is Cybersecurity for Precision Time Protocol. So special thanks to, I'm at Marist College as an undergraduate senior. I was participating in the Marist IBM Joint Study Program, and we were also working with Meinberg USA. So, little overview. We all kind of know what Precision Time Protocol is, as is the follow-on to Network Time Protocol. But while we know, since PTP is faster than NTP, we've also realized in research that it is not as secure as NTP. And therefore, this is my presentation on how cyber attacks can destroy the timing and clock synchronization, which is really bad, especially since PTP is used in major forms of like telecommunication, the banks, Wall Street, all that stuff. So if your clock is broken, that can be really bad. So at Marist, we have our own enterprise computing resource lab, which is downstairs in one of our academic buildings known as the Hancock Center. And we have 4 servers and a switch that help run these cyber attacks that I will be presenting some of the results of. So we have a Meinberg Grandmaster server. We have a server that collects the data. We have one server that also sends all of these cyber attacks. And then we have one that gets all the cyber attacks hit. So in this research, we successfully completed 11 cyber attacks on SYN 1588 NICs. And the tests were automated using Python 3, TCP dump, PHT2sys, and PTP4L. And they were configured to work with the NICs that we received from a third-party company that actually another intern, not myself, received as a prototype, because they were building their own form of authentication TLV to block cyber attacks. So they gave us their prototype for free, and we're like, hey, can you test to see if our security actually works? So all the tests that we ran elapsed 10 minutes, and these were some of the results comparing with PTP4L, with the authentication TLV, and without. So the first attack that we ran was called our announced packet DoS attack, which is an attack that spams the network with announced packets without collision of sequence IDs. And we also, in the next attack, did it with intentional collision of sequence IDs to see if the sequence ID number of when the attacks were being sent would make a difference on the results in the data. But we actually realized that there was no change, and with PTP4L, there was the major disturbance. The attack worked. It was not good. But with and without the TLV was able to block the cyber attack, but we did find a bug, and we were able to go back to them and be like, hey, that's wrong. But without the authentication TLV, the cyber attack worked. And then next attack that we did was our empty announced packet DoS attack, which is an attack that basically spams the network with empty packets, kind of similar to the last two, but rather than actually having data, we wanted to see if it would make any sort of difference in the results of the data. So performing on PTP4L caused a major disturbance even when the data packets were null. But with and without the auth TLV, actually, they were actually seen on the logs, but nothing happened, meaning that it made no difference on their auth TLV. So our next attack was our master spoof DoS attack, which mimics the announce and response from the authentic master server. So on PTP4L, a rogue grandmaster was created, and it sent announce and sync messages at a much faster rate than the real grandmaster, causing it to be disrupted even more than the last time. Then with the authentication TLV, it was able to block the security, and without the authentication TLV, it was able to it was blocking the security, since with their form of the code that they wrote, they were looking for sequential sequence IDs, and since there was not sequential sequence IDs, nothing was happening, and they were automatically discarding it. So it worked. So our next attack was our master clock takeover attack, which is an attack that creates a fake master clock with perfect attributes to attempt to make all PTP devices respond to it as a master. So for PTP4L, the service was rendered unresponsive, but PHT2sys still displayed normal offset changes and acted as normal. It accepted packets in modified time with a really wide range of correction values, and follow-up messages were sent outside of the control of the attack program, and kind of similar to the attacks before, with and without the authentication TLV. With the authentication TLV, we were able to, with the sequence IDs, it did not actually work with the sense of the sequence ID number count, but we did find a bug, which we were able to go back because 2 sync messages actually did go through when they weren't supposed to. So we were like, hey, that's a bug, go fix that. And then without the auth TLV, it took over, was bad. So our next attack was our man-in-the-middle injection attack, which is an attack that sends spoofed packets with injected correction field data. And we were actually only able to successfully complete this using PTP4L. I think with their hardware in the NIC, it was not cooperating with our auth TLV, but I know that is still being reevaluated and in the works. So hopefully at another time that we will have that correct data. So we can see based on the correction field values, whether it's like large correction field or small correction field, we have 2 very different results that produce. So our next attack is our clock frequency manipulation attack. And from PTP4L, we can see the regular output and then the fallout output. The fallout output is basically what happens after the attack actually finished. So we can see, again, it's still, even after the attack finished, it is not able to get back in synchronized with the time. And it was just getting worse and worse, actually. So then with and without the auth TLV, again, kind of like the attacks from before, without the auth TLV, the attack worked, it was bad. With the authentication TLV, it mostly blocked, except we did find 2 bugs, which we were able to go back and be like, hey, that doesn't work. So our next 2 attacks, which is our announce packet covert channel, we did covert channel attacks in the announce, delay, and sync covert, within the different packet headers. And one of the other attacks, which is pretty much the same guidelines as the announce packet covert channel attack, it is when you produce data, when you send packet, when you put a lot of information into either the Grandmaster clock ID or the Grandmaster clock accuracy packet headers, and to see if the data will still travel in a covert channel, in which if a covert channel is basically when data is being passed through when you can't actually see it happening. So you don't want covert channels. They're bad, because then you don't know that you're actually getting hit with a cyber attack. So as I showed in a little table, if it's red, it means there was a covert channel or there was a data injection attack that we were able to successfully complete. If it's green, there was no covert channel or there was no data injection attack that we were able to successfully complete. And if it's yellow, it means it's not fully covert, but because there is an exfiltration possible, which means it does need to be further looked into. So then we can see with the delay and actually the sync packets, they have the same headers and not actually the same packet headers as an announce packet, because all packets have different types of headers. But the results in the end were actually the same. So actually those 3 covert channel attacks were fit into a framework for the MITRE ATT&CK framework, T1048-003, and our procedure was listed as an example. Hopefully it's actually there. We all know how long sometimes those can take for them to update. So our next steps for this project is updating NTS into PTP. So the IETF conducted a threat analysis and eventually created a draft to put NTP into PTP. But we've been actually working with 2 people, I believe out in Europe, couldn't tell you their names right now. They've been doing their postdoc research on creating an implementation for PTP, NTS into PTP, And it would overall make this security even stronger, as there's nothing in secret with NTP or PTP traffic, and the general overall idea is to use TLS to distribute symmetric keys used for actual time protocol traffic. So some benefits to have NTS for PTP rather than NTS for NTP. So there are several reasons, including it reuses a lot of the existing infrastructure, really won't have to change much. It also allows for common security infrastructure for both NTP and PTP. TLS is already present on most devices. It's pretty much, if you have HTTPS, you can support NTS and you can support PTP. It does not require MACsec or IPsec. It has a much better flexibility. TLS cipher selection is adaptable, and NTS has flexible configuration options, which is good because obviously each person might have some different use cases, and flexibility is important for those. So here's a little overview on how NTS for PTP works. The PTP payload is added to existing NTS key exchange protocol. It has support for both multicast and unicast. And auth-TLV, as defined before in 1588 standard, is used to secure the PTP traffic. So, and I have two little pictures to just kind of show how the PTP instance interacts with the NTS server and sends requests and grants and then back to the actual network. So all in all, our little call to action is, once we have this implementation of the NTS into PTP, which actually another intern took over my position and is working on this, we would like to rerun all of these 11 cyber attacks and see if this actually works. We are, as a university, we are always looking to collaborate with other people, as I collaborate with IBM on a daily basis, as we are 10 minutes from the road from each other, but we also work with Meinberg. They're based out in Germany, but they have other locations in the area. We're always looking to collaborate. And so if you'd like to collaborate, I know it's so great to collaborate with universities because the younger generations can have such great ideas. And other additional information that we have is we have our GitHub repo and then just a link to the IEEE, some documentation. So thank you. And if there's any questions.
Thank you, Lillian. So let's go for some questions.
I'll try.
Kevin.
Great work. That's really important work. I'm really glad to see that was done. On the TLVs for security, maybe I missed it. Did you use both the end-to-end and the hop-by-hop TLVs for protecting correction fields from switches and so on?
I believe so, yes.
Okay. Great, thanks.
Yeah.
Go ahead, Rodney. Yeah.
So I guess one clarification, great research. It's awesome. For the off-TLV testing that you did, I noticed there were some bugs in what I assume is the implementation of the off-TLV. But
yes.
Did you find any flaws in the off-TLV itself where it was like missing certain attacks or anything like that?
It was mostly with the bugs. I will say it took a little bit to figure out the hardware configuration with our setup, but obviously we only ran 11 cyber attacks, and there's millions of cyber attacks out there, so you really never know until the more attacks you run, and that's how you kind of find those types of things. Thank you.